My name is Dezso Varga. So at our institute, we have established a detector physics group a bit more than 10 years ago. And this was established at the high energy physics department, which I'm heading. And the institute has been renamed to this HUNREN, which is Hungarian Research Network, which has been very recently established to somehow take better control over the institutions, to make sure that the institutions are having the possibility to pursue the highest level of research. Let's hope this works out. The overview of my talk would be an introduction first about muography or muon imaging, cosmic muon imaging. It is becoming a research field. It's becoming something which is not only just independent ideas somehow put together, which you can find here and there in the literature once every decade, but there's a community around that. I would like to explain some of the physics which is related to cosmic muon imaging, various applications, including underground and mining applications and detector operations and these kind of details which make it a practical thing. Muography, it's imaging with cosmic muons. It's a funny word. It became kind of being used in the last 4 or 5 years. Before it was called muon radiography, or it had some funny names. And muography is kind of a correct word. Imaging with muons. So muon radiography doesn't have any meanings because radiography is using X-rays. But this is now getting a sort of a common word for that. It is exactly what you would think and what is sort of known for many, many decades, right? That cosmic muons have a high penetration power. So if you put a detector somewhere underground, you can make an image about what is above the detector. I would like to show you a few examples here from the János Underground Research Laboratory. And I was very glad to hear that Gergely will introduce that laboratory in detail. It's a very interesting, funny laboratory. Sorry, it's a little bit made a mistake here on the slide. It has a vertical shaft, which is 30 meters. And then at 10, 20, and 30 meters depths, there are some tunnels and kind of access corridors where one can use equipment, one can install measurements. And we have done a measurement such that we have put a cosmic imaging detector, okay, so a detector which is able to measure the angular distribution of cosmic muons, cosmic particles, and we have put it at 10, 20, and 30 meters depths, okay? And if we put it at 10-meter depths, one can see the entrance, which is a very solid concrete structure. The left side is a simulation, what we expect. We expect the shadow of the concrete entrance part. And the right is the measurement. So this was the measurement where we could nicely see the structure. And if we went to 20-meter depths, we could nicely see the corridor, which was above, that is at 10-meter level. So we were expecting that the corridor, which was above, would have an increased muon flux because it's kind of a missing material there. And so this is the measurement. And from 30 meters, we would expect similar thing. The geometry becomes a bit strange. It has 3 galleries, so one can look at the 20-meter depths. So this structure would be the corridor, which is at 20-meter depths, seen from 30 meters. Okay, a little bit complicated geometry, but one can nicely see it in the image of cosmic muons. Okay, this was done with a relatively small detector in our preliminary version, and we're very, very happy about that. So this means that indeed, we can measure structure, 3-dimensional structure of objects if we place something below that. There's a lot of applications around muography. If you look at the literature, it has, on one hand, a very, very long literature. Already in the 70s, Alvarez made a measurement. You might have heard about that. Searching for hidden chambers in a pyramid. Funnily, it has been more or less repeated in 2018 in the Great Pyramid, and they have found hidden chamber. They have also found another hidden chamber above the entrance. And that one was funny because they could identify that very precisely up to the point that, you know, Egyptologists, they don't want to touch these things. But they were so convinced that they were managing to bring a little camera inside the structure, and they have seen a new cavity which was not touched for like 4,000 years. The first time that ever a person sees that has been identified. So these are nice results and breakthroughs. This was a very interesting measurement at the Fukushima reactor after the disaster. They were putting sheets of emulsion detectors, which were possible to use as a tracking device. So in an emulsion layer, they could register single muons, they could scan that. It's a pretty serious machinery behind that, which is originating from neutrino physics. But they could do that at Fukushima, and they could nicely identify that. So the one which was not melted, or which was intact, had the core, but the one which was probably melted down was simply missing the core from the place where it should have been. And there's no other way to look into the meltdown core at the Fukushima reactor. If you think about it, which are the applications which are sort of not only just catching your thoughts, but have money in there, okay? And mining is an industry where there's a lot of money. And indeed, there were quite a few breakthrough results. There was a group in Canada, as well as in they were making measurements also in Australia, and in the United States, they were trying to make measurements. And this is an example where they could identify high-density deposit, mostly uranium deposit, in a mine. And this was a known deposit, so the miners actually wanted to verify this such that they didn't tell where this deposit is expected to be, but were just requesting the measurement to be done, which could correctly identify the high-density region above the measurement. So they went like 400 meters or up to 600 meters depth, and they had a detector, scintillator detectors, which were kind of a size of a train car. They were bringing it down into the existing galleries, and they could make measurement again about the structure which was above. So you need to access below. That's a fundamental limitation. And I was trying to give a little bit of a personal historical overview of what happened over the many years. If people try to look back, how did it really develop to the point where we are today? So there were the first measurements literally half a century ago, where they could immediately identify this possibility that this is kind of a working idea, but the instrumentation was so oversized that it was totally impractical. So after the discoveries, they didn't quite continue. And there was a span of at least 2 decades. Then in the 90s, particularly in Los Alamos, there was a very quick development of various possibilities, which included scattering muon imaging, which is that you have an object, and if you not only place the muon detector below, just to measure how much muon it absorbs, but you put also above, then you can measure the trajectory which comes in, which goes through, and so it scatters inside the object. And this way you can measure particularly the high atomic number materials, because scattering is more sensitive to atomic number rather than density. And then around the turn of the century, around 2000, there were very serious breakthroughs in the sense that they could identify such very important findings, in particular in volcanology, that if you're imaging a volcano, so if you put a detector next to a volcano and it's looking at that, it has to be at some elevation angle, but still if it looks at that, it is possible to see what's happening inside a volcano, which was totally impossible with other means. So volcanology is a very complex search, extremely complex, and they have very limited tools. You know, they measure how much the earth shakes, but it always shakes. It's always earthquakes all the time. How much gas is emanated, but there's always some plumes and stuff. So they could not really make very clear correlation between activity and eruption sequence. And so this was pretty an interesting study. And now we are practically in the fourth generations, where what happened was that there were industrial companies, industrially interested companies, which entered kind of a competitive market, and they were really looking for solutions to apply this technique, which required a drastic decrease on the cost, and at the same time a drastically increase on the reliability of these devices. So it's not anymore scientific devices which one puts here and there, but really usable, practically usable and deployable systems. So what one now in this era, so it's interesting if you look at that. I mean, people were working on that for half a century. There's very rarely a research science where you can develop some idea over a half a century. It's a very strange. And the reason is that now detectors are much higher efficiency resolution, much more reliable and much more cost efficient, partially due to the readout electronics. Detector technologies are interesting for those ones like myself who are developing detectors. I'm coming from particle physics and not geoscience, not engineering, not any of these volcanology or things. We are very much interested in how this detection is done, what's the detection efficiency. But it turns out that geoscientists, for example, they totally don't care how we are doing it. But what they are interested in is what we are doing. So on the side of technologies, there's basically three technologies which emerged. One is emulsions, which is thick photographic films. You might have heard about it. It's very interesting, very, very old stuff, but it's still very much usable as of today because in neutrino detectors, they have developed very good quality emulsion films, very easy to handle. It's very, very convenient. It doesn't have any time resolutions. You cannot monitor things. You have to retrieve the thing after the measurement, but that's just one limitation. Scintillators are very, very popular because they are very high efficiency and very reliable. And gaseous detectors, which are good efficiency, has a very good cost efficiency, but somewhat more complex than the scintillators. So our expertise in gaseous detectors. And since we are kind of focused in this direction, I wouldn't like to talk about the other two, but those are equally competitive. So we're definitely not in a place of trying to make which kind of judgment which is better or worse. You cannot answer that question because it's too complicated. There's a huge range of costs for scintillators. Okay. There's a, let's say, span of 2 orders of magnitude, depending on the quality of you require. And same for gaseous detectors and also for emulsions. So more or less, these things are similar cost. One cannot say that any of them would be drastically more costly than the others. And there's additional costs like deployment. So if you have 10 minutes, yeah, if you go to Fukushima and you have 10 minutes, really your safety people are counting that. You have to go in there, install something, and get out. Probably there's nothing else than an emulsion film, okay? Or in that case, they had like a little slice of 5 centimeters where they had to stick it in. It's not so easy to find anything, but otherwise, there's a lot of additional costs, which overall makes it. It's a complicated question, but yeah, it's one of the important questions of the whole thing. So let me introduce the gaseous detectors. This is where our expertise came, and this is where we are good at. So I need to remark that whenever it comes to muography, the ones who are using these, they don't care what kind of technology is being used, okay? So whenever I'm talking about gaseous detectors, because that's where expertise is. But if it turns out that this is not usable for any purpose, we don't mind. It's just a tool. We are looking for the purpose, which is usually much more interesting. So the good about that is that one can make good precision tracking. So you can really precisely make a measurement of every single muon which goes through your detector. We have very good angular resolution, usually well below a degree. For example, at the scan pyramid measurement, one of the detector set was gaseous detectors, French built. They have built a beautiful device which was looking at the pyramid from the outside. We have built detectors at Sakurajima in Japan. I will talk a little bit in detail. What one has to know about gaseous detectors, there's no simple thing existing. There's no simple gaseous detector existing. Okay, by definition, it's more or less a complex device which has to be constructed. At our group, the detector physics group is mainly dealing with high energy physics instrumentation. Okay, so we are part of CERN. Now the DRD1 collaboration as well as previously the RD51, which is developing high performance gaseous detectors for fundamental physics. We are part of CERN and A61 and the ALICE collaborations, as well as we used to be part of the ESS for a neutron detector development. So these are all fundamental sciences. And one of our activities, one of our focusing directions was muography, where we were trying to engage in a number of applications using our existing expertise. And here I'm showing a number of things which are related to that. So it has to do a lot of expertise from fundamental science. We have a nice observatory at the Sakurajima volcano. We have mining applications which we work on. In Hungary, there are nice caves. So speleology is an interesting subject, and some others. It's just an overview. What kind of detectors can we use for cosmic muon imaging? So the fundamental problem in cosmic muon imaging is that you want to have large surface, because some small detectors won't give you an image. And we have developed detectors, MWPCs, which were relatively classical in many sense, but we're trying to use contemporary design and contemporary materials. So much simpler than those used to be in the 70s or 80s. And pretty reliable. We have built more than 150 square meters over the last years. Half of that is at the Sakurajima Observatory. This is one image in the flat table. It's being glued, and it's a little bit manual. Unfortunately, it's a bit manual and professional work which is needed. I hope you see this image on the right. It's a bit hazy. I'm showing here the tracking efficiency with the probability that this detector gives a valid measurement point with a typically 1 centimeter precision over this nearly 1 square meter. And this starts at 90% and up to 100. So the typical efficiency is around 98, 99% for capturing 1 point on the track. A typical large size detector would be we have a design which is kind of 80 by 80 centimeter, a little bit smaller in sensitive area. The efficiency is very high. And this is a kind of image about one single event, okay, one single cosmic muon event. Here you have 8 chambers, 8 individual detectors on top of each other. And when a cosmic muon crosses, these axes show the hit, the wires which gave a hit, so which gave a signal. So dots correspond to zeros and axes correspond to 1. And you can see a very clear straight line which corresponds to a muon. And this funny thing was probably a secondary electron which was created either by the muon or was coming from some kind of a secondary interaction. One of our most relevant applications where we were collaborating with the University of Tokyo to build an imaging system at the Sakurajima volcano. At the time of the conception, which was 2015, Sakurajima was very active. And next to that, there's a city called Kagoshima, which has 1 million people around that. So it's a pretty urbanized area and was posing a very large risk, which was socially relevant. It was interesting that later on, over the years, Sakurajima started to sort of quiet down. But since the funding was available, the observatory has been constructed. So this is the Sakurajima volcano in the background on a very quiet day. This is the building of the observatory. And inside the observatory, we have installed modules. Each module was typically a half a square meter or 1 square meter. So this is one module. And now it's more than 8 square meters in total sensitive area, tracking sensitive area, which is the largest of the world. It's about 3 times larger than the existing now at Vesuvius. Italians have made a very nice detector system at the Vesuvius Muraves collaboration. Data acquisition was based on a single Raspberry Pi for each module. We have built triggering system, high voltage system, all kinds of detector signals. Since we couldn't find a good readout front-end and readout system on the market, we had to develop it from our own earlier experience. It's a rather efficient system, and so includes the coincidence as well as the data taking, and the total amount of data is relatively low, so like a few tens of megabytes per day with a full efficiency, so capturing every single muon. I would like to introduce underground detectors. Underground detectors, we had to understand that here there's always a very, very important compromise between size, and possibilities, which local possibilities. So the idea is that one has to use the largest size which fits to the specific applications, and for that reason we have built different. So this one is, for example, large version. This is the smaller version. Whenever we had place to access, we have put the large one, okay? And if there was no possibility to access something, we had to use smaller units, more compact ones. So built a set of detectors. What we had to understand, it took us many years, that one is building a nice detector in the lab. It's beautiful, it's quiet. Yeah, you have a nice coffee and look at the data and stuff. But if you go underground into a mine, so this right image, same person, same detector in a mine in Finland, things are totally different, very, very much different. So we had to very much learn how to make those detectors not only survive the travel to the place, sending to Japan, or traveling underground into a mine and installation, but on the long term to survive and make usable data. Here I'm showing you a few case examples. One left, two images from a mine in Germany. Here, the detector was placed under a vertical shaft. And what you see is that the shaft, which is capturing much less muons, is really shining. It practically lets most of the muons through. Okay, so you see this is the X and Y angular slope of the tracks. And this image is if you put the detector a little bit off next to the shaft, you still see the shaft structure, but from the side. So it's a very nice, very clean image of a known structure, a known vertical structure. On the right side, it's a mine, Finland, where it was contracted by a company which we were in collaboration. So unfortunately, we couldn't disclose even direction or location of that. We were allowed to show this image, which is the cosmic muon flux, the amount of muons per square centimeter per second, which is on the level of 0.1 in that depth, 270-meter depth. And one can see a very clear image, partially of the surface structure, and partially, if one looks more clearly, about the underground density they were looking for in the mine. Where's the granite and where's the ore? They were interested in about the surface of the contact of the two. You will find my slides. If one looks at as a function of depth, cosmic muon number drastically goes down. So one needs pretty large detectors to have a meaningful measurement. And I have a few examples about, so this is a measurement in the Buddha castle of a tunnel which was above the measurement point, pretty nicely visible, and some three-dimensional tomography. Here I put the reference, a recent paper which we have completed. And okay, I had a remark about air showers, but that's not so necessary. So as a summary, muography is becoming a research field because of contemporary technology and detector construction methods, okay? And at our detector group, we have extensive collaboration with industrial partners and international partners. We have multiple Horizon Europe and H2020 projects. Why it can be relevant for CREDO? Because the detectors which we make are potentially cost-efficient and reasonably large-size detectors in the order of a few dollars per square centimeter. I've seen these nice tiny things. So in that sense, if detector is larger, it may still be pretty much cost-efficient. So thank you very much.
we can have short questions.
Thank you for your lecture. It was very interesting in my area too. But I have a question to the last slide. This cost $1 per square centimeters is cost of detection part or detector with full electron?
Yeah, with everything.
With everything.
Okay, another question.
Okay. Yes, very interesting presentation. Same
Thank
comes
you.
from me. I have many questions, but I don't want to take too much time. Did you by yourself did any research using scattering?
We have done some measurements related to scattering, but it's not yet published and it didn't really come out.
On the large objects, or what was it?
Relatively small objects. Here I'm showing, for example, this is a scattering experiment where we had, this is an image like 50 by 50 centimeters, and this is a steel plate of 3 centimeters thickness, 20 by 20, and this is a small lead block. So object like that. So we have the detectors of these 80 by 80 centimeters one. So the sensitive volume is like 50 by 50 by 40 centimeters or so.
Okay. Thanks.
So that's an interesting thing, but there's a lot of groups dealing with that. So, and we didn't think we can really contribute to the field. So we need some time to improve measurements, and then probably we can continue that. Interesting field.
Thank you. So let's remind you that we have the round table in the evening, so we can also discuss any of these matters. If there are no more questions, no questions.
There's some question from the end.
Short. The last slide with the summary. The cost $1 per centimeter squared. Is it together with electronics?
Yes.
All together?
Well, it's a whole unit. So what I did is I was trying to estimate the cost of a full system like that divided by the area.
Okay, so
Area or this is size of all detectors or one effective?
One effective detector, and here it's a very good quality tracking. I don't want to go into details, like 8 detectors, but for very clear muon measurement, you need 3 maybe or 4. You don't need a full size. So I was estimating to have 4 detectors of this size, roughly of that order. I'm not sure that it's $1 or $2 per square centimeter, but not very large. My point was that these are not very large numbers, considering the fact that one doesn't work with a very small detector, but already a large one. Altogether, it's not cheap, multiple thousands of euros or thousands of dollars. But one unit gives you like 100, a typical detector on surface gives 50 muon tracks per second.
I would like to talk with you later in the free time about parameters, about time resolution, etc. Okay?
Okay.
Thank you. That was very interesting. Let's
Thank you very much.
Speaker again.